Right, morning all. So this lesson is the next one in our forces and motion unit. So this lesson is on forces and braking. So today we are going to be looking at stopping distance, and the idea of that stopping distance is made up of a couple of components. So we're going to understand about what those are and how we can calculate those things. We're going to be looking at factors that will affect the stopping distance for a vehicle, and then we're going to want to understand what the how the brakes end up stocking a vehicle, so how the brakes relate to reducing the kinetic energy of a vehicle, and then after having reduced that kinetic energy, about where that energy is going to be transferred to. So first thing today is I want you to consider this question here. So we've got a car over here, and I would like you to think about what forces, and note the plural there, are going to be acting against the forward movement of the car. So pause the video for a moment and have a think about which forces they would be. So I'm sure you identified friction as being one of the forces. That is, of course, the force between the car and the road. Next one, another frictional force. So we'll be thinking about the air resistance between the car and the air, the medium that it's moving through. And then the other one, which is only there when it is applied, would be the braking force. So there we're thinking about the force between, between the brakes and the wheel. So there's a video link down here, and I will put that and show my homework for you, and I'd like you to watch that. It's only a minute or so long. So next we're going to consider what stopping distance is and about what the two components are that actually make it up. So stopping distance overall is the distance that it takes a car to stop when from when you see an issue to when you come to a complete stop. So the first component that we need to think about here is the thinking distance. And so the thinking distance is the distance that's going to be travelled by a vehicle during the driver's reaction time. So if Finn was to walk out in front of the car, then what would happen is that the car driver would see Finn, and then it would take him a fraction of a second in order to be able to apply the brakes. Now that fraction of a second, the distance travelled during that time, is actually what we term the reaction time. Braking distance is the distance that once the person has seen Finn walk out into the road and actually starts to put the brakes on, to when the car comes to an absolute standstill. So it's that distance that's covered within that time frame. So to put it in more physics terms, it's the distance travelled by the vehicle under the braking force. So here in this image we can see that all represented quite nicely. So we've got that the car is driving along. At this point it detects the hazard, which is the moose in the road, and during the time that that person, the driver, has detected the difference and applies the brakes, the car travels this distance. So that's the thinking distance. Braking is applied, and so the car begins to slow down and then comes to a standstill. That distance there is, of course, the braking distance. Right, so I'd like you to have a look at this data. So when you learn to drive, one of the things that you'll have to look at and learn about is the highway code. This is an image taken from the highway code, and what we've got is we've got different speeds, and so we see 20 up to 70 miles an hour, and then we've got the distances that the car travels during thinking distance and braking distance represented in two different colours. So I'd like you to have a look at this data here, and I'd like you to pause the video and consider this question. What is the trend in this data? So I hope that you picked up that there are a couple of trends in this data. One of the trends is relatively easy to describe. That is some complicated mathematical language that we might want to associate with it. The other trend is a little bit more complicated to describe. Nonetheless, first trend. I think you would have picked up the fact that the thinking distance gets bigger as the speed increases. What we can say is we can apply some actual quantities to that, so we can put some maths along with it. So we can see that when we go from 20 miles an hour to 30 miles an hour, which is 10 mile an hour increase, the distance increases by 3 meters. The same happens when we go from 30 to 40, so 9 to 12 is 3 meters, and the same when we go from 40 to 50, also 3 meters. You can see that pattern throughout. So for every 10 mile an hour increase in speed, we get the thinking distance increases by 3 meters. Therefore, we can say that there is a proportional relationship between the two. And look, if we increase the speed from 20 to 40, so we double the speed, the distance also doubles. If we go from 30 to 60, the distance also doubles. So there's that clear, directly proportional relationship between these two values. When we look at the braking distance, now we can see that's a little bit more complicated because it doesn't go up by the same amount each time. So this one goes from 6 to 14, which is 8 meters, 14 to 24, which is 10 meters, 24 to 38, which is 14 meters, and so we can see that each time the distance is increasing by a greater amount. So for every 10 mile an hour increase in speed, the distance increases by a larger amount. So we wouldn't say that that is a directly proportional relationship. However, there is a relationship there which is positive, but it's also just a bit more complicated. So this is going to help us to visualize the relationship between thinking distance and stopping distance and braking distance and speed, and it's also going to allow us to put some numbers on the actual relationship between speed and braking distance. So first thing that we want to pick out is that we've got, what we can see clearly from this graph is that both thinking distance, braking distance and stopping distance increase with speed. What we don't have is any evidence that they increase at the same rate. So if we consider first of all just thinking distance, then when we look at that line we can see that it's a straight line relationship, so we could talk about that being linear. And so the next thing that we could think about is, well, let's look what happens when we double the speed, so 20 to 40, we can see that the distance also doubles, so thinking distance doubles over that time. And the same when we go from 30 to 60, there is a clear doubling in the relationship. Therefore, we can talk about, number one, there being a linear relationship, and we can see linear means straight line, positive means that we've got a positive gradient on the graph, but then we've also got this idea that it is a directly proportional relationship because doubling the speed doubles the distance travelled. However, looking at braking distance, we can see much more clearly on this graph that the relationship between those two values is not a proportional relationship, because what we've got is we've got a curved line on that graph, and the curved line on that graph the curve increases, so the gradient increases as the speed increases, and so the line is getting steeper and steeper and steeper. What that means is that we don't have this straight line relationship, so it's not a linear relationship, but there is a positive relationship between the two, i.e. increasing the speed increases the braking distance. But what we can do is we can begin to consider numerically what happens. So look, if we take the speed and we double it, so times it by 2, we can see that the distance, the braking distance, increases from 6 to 24. So that is a 4 times increase. So if we say that we're increasing the distance by the speed by a factor of 2, if we square 2, that's 4. That gives us the increase in braking distance that we see. Let's just check that on this one. So if we go from 20 to 60, that's a 3 times increase. And so if we go, if we take 3 and we square it, that is of course 9, and 6 times 9 gives us that increase that we are looking for. So we have a relationship which is actually a squared relationship between the two factors. So we can summarize this in a simple equation that stopping distance is equal to thinking distance times by braking distance, and we have this second kind of factor that if we increase the speed, then the stopping distance is going to increase. And so if we think about that a vehicle has a fixed braking force, which is the amount of force that the car is going to be able to apply when you put on the brakes, then what that means is that the faster the car is travelling, the longer the stopping distance is going to be. So now we can move on to think about factors that will affect the thinking distance. So factors that are going to impact on the time that it takes someone to react and actually start applying brakes. So in biology homeostasis 1, we did that practical, or well, we looked at a practical where we could measure reaction time, which was the ruler drop exercise. Now, one of the things is that you'll remember from that is that people's reaction time varies. So some of you had faster reaction times than others. Now we can apply a value to that, and we can say that actually people's reaction times will vary from 0.2 seconds all the way up to 0.9 seconds. So we see natural variation in reaction time, so therefore we're going to see natural variation in the thinking distance, and so the distance covered by the car before the brakes are applied, but while the person is reacting to a perceived threat. So anything that affects your reactions can therefore affect your thinking time. So we can consider here reaction time. We can think about, therefore, if you're tired, a little tired this morning, so it's kind of impacting on my reaction time and my reactions. But we can also consider things like drugs and alcohol as things that will impact on somebody's reaction time and will slow it down. The other thing that we can think about is distractions. So if you are distracted whilst you are driving, maybe by your mobile phone or something like that, then your reaction time will also be affected, and so thinking distance will increase. So in short, we have natural variation in reaction time. Reaction time can be slowed down by tiredness, drugs, alcohol, and distraction. Now on here, there's a link to a YouTube video. I really encourage you to watch this. It's about distractions while you're driving, and it's really good in giving you a feeling of about how they can impact. So Our next factor that we want to think about is factors that will impact on braking distance. So we're going to work across a couple of slides here because there's a bit more and it's a little bit more complicated. So the first thing that we'd want to consider is the road and weather conditions. And so if the conditions of either of those are adverse, i.e. they're poor, they're not very good, then the braking distance will increase. So if the road is wet or icy, then that means that the braking distance will increase. We can apply the same idea to the condition of the vehicle. So if the vehicle has got warm brakes or warm tyres, so it's not in very good condition, then that's also going to impact on the braking distance. It's going to increase it. This is one of the reasons that we have MOTs and why it's so important that once you're driving, you actually maintain your car and buy new tyres for it and make sure you replace the brakes and things like that. So if there are poor conditions in either of these two situations, then that means that the car is going to take a longer distance to stop. And so we have a nice summary there of that process. So this is another nice animation for us to consider. So we're going to look at two different vehicles and we're going to have some gaps in our table, and I want you to fill in those gaps. Now there's a couple of ways that you can go about this. First one is you can pause the video in a second and you can put which values wherever you think that they may fit within the table. Your other option is I will share this PowerPoint with you as well, and so you could actually have a go at this physically as well on your own laptop by downloading this and showing my homework. So thinking distance first of all, that's our first set of relationships that we want to think about. And then we've got think about braking distance and then think about stopping distance. So pause the video now and put these numbers at the bottom in the different in the empty boxes. Okay, so here is the answers for you. So we can see clear relationship with our thinking distance here, so hopefully you picked up the fact that we've got that increase of 6 each time, so that allows you to put those numbers in. Now braking distance, we know we can do the relationship where we square our values, the increases, so you could have done it that way because 20 is 5 meters, whereas 40 will be, so we're doubling the speed, so therefore we're going to times the distance by 4, so 5 times 4 gives us 20, and if we go from 20 to 60, that's a 3 times increase, so we need to times by 9, so 5 times by 60 of course gives us 45. And then stopping distance, you're just adding those values together. So next thing to think about is a bit more physicsy, and it's about this idea of the greater the speed of the vehicle, the greater the braking distance will be. So we can expand that idea a little bit. So if the braking distance is going to be greater when the speed increases, there's a second thing that comes out. If we want to stop the car in the same distance, so say we went from 20 to 40 miles an hour, but still wanted to stop the car in the same distance, then if we applied a much larger braking force, then potentially we could stop the car in the same distance. So what we want to understand is, well, how do the brakes actually slow the car down? So key point here to consider is that when the brakes are applied to the wheel, then what's going to happen is that work is going to be done, energy is going to be transferred, because the brakes are going to grip onto the wheel, and so they're going to reduce the kinetic energy of that wheel. What that's going to do is it's going to slow the car down. But one of the things that we know is that energy can't be created or destroyed, so that energy has to be transferred somewhere, and so it gets transferred as thermal energy. Now what that means is that the brake temperature is going to increase, as we can see in this image here, and so we can extend that and think about that if we have a greater braking force as we would have in a sports car, like in this image, therefore we're going to have greater decelerations, and so the temperature of the brakes is going to increase more. So there's a consequence of this. When we're talking about very large decelerations like you would see in a race car, then you can end up with very large temperature changes, and so potentially your brakes can overheat and there will be a loss of control as a consequence. So this is a nice summary of the different factors that affect your thinking and braking distance. And our kind of final bits before we move to summing up would be these ones. So we can use that equation for final velocity and initial velocity relationship in order to be able to calculate either distance travelled or the acceleration, i.e. the deceleration of a vehicle. So if you have a look at this, we can see that v squared is equal to u squared, so final velocity is equal to initial velocity plus 2 times the acceleration, so deceleration in a braking situation, and the distance that it occurs across. So therefore, what we can say is that the velocity is going to equal 0, so 0 squared is 0, so that takes all of this out. So what that means is that if we want to work out the distance, then we need to do u squared divided by 2a, and it's going to be a minus value. We need to note there, and then a, the acceleration, which will be negative because it's a deceleration, will be u squared divided by 2s. The other equation that you can be asked to use in this section is F equals ma, so force equals mass times acceleration, and they could give you values for mass and acceleration in order to work out the braking force, or they could ask you to estimate the mass of the truck or the deceleration of the truck and then work it out. That, of course, would be a much higher level question. So, summary. Friction and air resistance are going to oppose the driving force of the vehicle. The stopping distance will depend on the sum of the thinking distance and the braking distance. So therefore, factors that affect the thinking distance, so poor reaction time, which could be due to tiredness, alcohol, drugs, or distractions like using a phone, along with high speed, would increase the thinking distance. And high speed, poor weather conditions, and poor vehicle maintenance would also all increase the braking distance as well. And we can use that force equals mass times acceleration to calculate the braking distance of a vehicle. Right, so I would like you to have a go at these questions. The questions are in the booklet, though they don't have the figure 2, so I've put that up here for you so that you can answer those. And here are the answers for those questions, so please work through and mark off the work that you've done there. Then there's a worksheet for you to do on Show My Homework. So here's some data for the table in that worksheet. So you can use this to do the calculations that you need to, and then answer the questions, please. And then here is the answers for those questions on that worksheet. So mark those, please. And then I would like you to submit photos of your 2 sets of questions there for me, please. Thank you very much. I hope that's been useful. I will see you for a live lesson again next week. Have a good week, and I will catch you again next week. Bye-bye.